All right, so the question is, this function, which I called Bob. If you didn't see the last recording, well, bad for you. I called this function Bob. It was very amusing, I swear. I'm funny. Anyways, um, Bob function over here. So, as you said, Aditya, you take the same input point, x, and with a regular function, you would put it into an expression like x squared and get out an output value, which we often call y, or f of x. With the Bob function, what you're doing is you're taking that same input value, -2, and instead you're getting the rate of change here, m. And the way that you denote that, you don't say, you don't need to denote x or y like a pair. You just write either f prime of x or dy by dx. Because if you think about it, like that resembles this delta y over delta x, right? And that's what we're looking for, the slope. Yeah. M slope is usually delta y over delta x, except in this case, it's a very tiny change in x and a very tiny change in y. So that's why we have like this special notation. So we use this notation when we have like an equation like y is equal to x squared. This notation when we have a f of x, like a function notation. Does that make sense?
Yeah.
All right, cool. Any other questions before we move on to finding the magical Bob formula? Someone's going to be watching this afterwards. They're like, what the hell is Bob? What are you talking about? Anyways, so we need a rule. We need some kind of rules so that we can go from x squared to the Bob equation. So whatever equation Bob is, I'm going to stop calling it Bob. So for real, f prime at x. So go from f of x to f prime at x, or go from y to dy by dx. Those are the fancy math words. Yeah, we're going to use those from now on. So this rule, I'm going to tell you what it is. It's called the power rule. I'm not going to explain it to you. So I absolutely hate to be doing this. I literally prepared this lesson, and for 15 minutes I was just sitting here like, do I explain this to them? Do I not explain this to them? Do I explain it to them? So here's what I've concluded, okay? This power rule, the thing that we need to get from f of x to f prime of x, so go from this expression to some expression that will give us from input to the rate of change, the rate of change at one point, or how much the output changes with a tiny change in input. That is what the power rule does. Unfortunately, I can tell you what the power rule is. I just can't tell you why the power rule is. Because to tell you why, I need you to understand these three things: exponent laws, limits, and binomial theorem. Now, limits is fine. I actually explained limits, except I had to cut it short for time. Exponent laws, I'm literally going to teach it to you right after, just for review. This thing is just so horrendous, okay? I'm not even going to lie to you. To understand this, you need to understand geometric series, which is a thing. It's a big word that I just randomly named, but it's a thing. You need to understand how combinatorics works, another big fancy word. And I unfortunately do not have time to explain that to you. So I hate to do this, but for now, I'm just going to give you the formula, though I will link to every single video you would need to know to understand why the formula is what it is. Okay? Does that sound fair? All right. So without further ado, let me tell you what the power rule is, though if you want a proof of that, you'll have to do your own digging afterwards. I'll give you resources to start. So here's another form of what we said above, d by dx. In this case, we hadn't defined y is equal to x squared. So what we can do is we can actually just put, d blank by dx. And then we have like these square brackets, which are like, oh yeah, like we don't have a y because we didn't define it, unlike up here. So just put this stuff in the brackets, like in here. Yeah. So power rule is for any formula like x squared, any formula where you have an exponent, and it's in the form ax to the n. So like, 2x, yeah, 2x to the 3. Yeah. So what the power rule says is if you have an expression like 2x to the 3 and you want to get a function where you can just get the derivative at any one point, the rate of change, then what you do is first you take this exponent n, so 3, you bring it out front, and then you multiply it by whatever original thing you had. So 3 times over here, a was 2, x, except the one change you got to make is whatever the exponent was, decrease it by 1. So 3 times 2x squared. Again, 2 is a, x, and then 3 is n. You take the 3, the exponents, and you multiply it up front. Then you take whatever you had before, ax, except the exponent you had before, subtracted by 1. Okay? This is a rule. You can understand why, but you got to know these 3 things. So I will link the videos you need to know in the description, or if you don't care, you can just memorize this. Because the key thing is not calculating these derivatives. In machine learning, this is the key thing you need to understand, which I spent so much time on last video. This is just, oh, I'm watching a video. I can't follow along what they're doing. If you want to follow along, then you can use this. So let's just do a few quick examples. So d by dx, that's what this reads, d by dx of x squared. Again, we don't have the y defined. If we had a y defined, we could just say, like we do over here, dy by dx. So this square bracket thing just means shove whatever you have here as if you had like a y. Yeah? So d by dx, look at our rule again. Take the exponent, so take 2 and multiply it up front. 2 goes up front. Then multiply it by whatever you had before. So in this case, this isn't like, just x squared. It's really 1 times x squared. You see how that's still the same? So it's like 2 times 1. The reason I add that is because 1 is the a in this case. 2 times 1 times x. And before it was squared, now it's just x to the 1. Because we reduced the exponent by 1. Making sense? So 2 times 1, x to the 1. X to the 1 is just x. So it's just 2x. That's the derivative. Remember what we're saying again? We're saying we're getting an equation where we take any number x, and if we put it into this function 2x, then we will get the rate of change at that point. And remember, hey, that makes sense because we just calculated the rate of change. So here we had the input value was -2, right? And we did the math last lesson. We calculated that the rate of change at that one point was -4. Well, hey, take a look. We just got that the derivative function is 2x. So if we take the input, put it into the derivative function, we should get this number, -4. So here we take 2, put in -2. That's the input. That's the point right here, -2. And lo and behold, 2 times -2, that is -4. You guys see what this function is doing? It's taking the input that we got on the x-axis. Then, instead of getting the output back, we're getting the slope at that point back. Cool? Yeah? Come on, let's do it one more time. Aditya still doesn't like it. I'm sorry. I know this is in your lesson. All right. Here, I just changed the variable just for fun. You can do that. It doesn't need to be, X all the time, whatever. So, let someone else guide me through it. Remember the three rules? What do we do? Want to guide me through the process of following this formula?
You take the exponent and put it at first,
Up front. Got it.
the brackets,
Mm-hmm.
and then you put the coefficient, so
That's
5,
the A value. Yep.
and then the z to the power of 4 minus 1, which is 3.
You got it. So 4 times 5 is, in this case, 20. And then you have z to the 3. There we go. There's our second one done. Yay! You just calculated your second derivative. Again, I know random rule. I don't like random rules, but I will link to the videos you need to know to be able to understand this. Before we go on to the next example, quick mini recap of exponents if you don't remember your laws. This is like the 1 plus 1 of math. So yeah, why is it the way it is? 1 plus 1 equals 2. Math they just decided, yeah, that's what we want to do. So anything raised to the power of 0 is equal to 1. That's one exponential law. And then if you have 1 divided by x to the n, that's equal to x to the negative n. That's another exponential law. I hate telling you to memorize things. Honestly, I do. I wish I could explain it to you, but binomial, like, just blame it on binomial theorem, okay? If it weren't for binomial theorem, we would be having so much fun. It's just this binomial theorem is the party pooper. And exponential rule. I will give you an intuition for this one. So when we're saying like x to the 2, like 5 to the 5 squared, then we're saying, okay, 5 times 5. So if we have like 5 to the negative 2, it's like 1 over 5 times 1 over 5. That makes sense, right? Come on, that makes sense. That makes a little bit of sense. It's like, there's some intuition there, but yeah, we need to memorize these two things. All right, let's move on to the third example. D by dx of just 7. Wait a minute. What? Wait, where's the x? There's no x. Why is there an x? Let me tell you something, okay? This is like genius right here. The x is hiding. It's hiding, and it's got to do with one of these two rules. You know which one? Aditya?
Since x to the power of 0 is 1,
Mm-hmm.
probably the hiding x has a power of 0, making it 1. So
Yeah,
7 times 1 is 7.
7 times 1 is exactly 7. So this still works, all right? Here's what we got to do. So as ever, take the exponent, move it out front, 0 times, I don't even care at this point. I literally don't, but if you wanted to, 7x to the negative 1. Again, understand, this just means 7 over x to the 1. But it doesn't matter because you're multiplying by 0. So in the end, it's always 0. This is what happens with any constant you see. If it's ever being multiplied by x to the 0, which is for like in an equation like y is equal to y equals 2x plus, let's say, 1. So this 1, it would always just, if we said dy by dx of this, then the 1 would not affect anything because it's just a constant. It's just being multiplied by x to the 0. Yeah? So whenever we're taking the derivative of a constant, it's always 0. And remember, that makes sense. What is a derivative? It's how much the output changes with a tiny change in the input. Well, you literally cannot change a constant. It is a constant. That's the definition. So it makes sense that the derivative, how much the output changes, is 0 because the input can't even change. Yeah? All right. Last example. So over here, we are now doing d by db. Again, I switched up the variables. You can do that, why not? D by dB, what is it? Well, this one looks a little bit odd to me. I don't like the way this is expressed. So I'm going to use my handy rule right here. Again, the entire reason we're doing this is because if you want to follow along in proofs, then you need this. When they're teaching you like an Android ML course on Coursera, you'll need to know this. So instead of writing d by db of 1 over b to the 4, I'm just going to put b to the negative 4. Remember, that's what the rule is. 1 over something raised to the n is equal to that to the negative n. Cool? All right? Not all right? All right. So here, now, this is in a form we know. Let's see, who am I going to pick on? Arjun, you're looking at awfully quiet today. Would you like to volunteer?
Okay, I'll
So,
try. So,
mhm.
it's gonna be -4
All right.
times a bracket, b,
All right.
I don't remember anything else.
That's fine.
Oh, to the power of -5.
Hell yeah, you got it. To the negative 5. Yeah, that's my 5. Remember, it's almost like there's an imaginary 1 here. So it's like 1 times b to the negative 4. It's like you do have a 1 times b to the negative 5, but it doesn't affect anything. In the end, the answer we get is -4 b to the negative 5, which is equal to -4 times 1 over b to the 5. All right, cool? Yeah, just boring stuff over with. Just got to memorize one formula. And if you're so inclined, learn binomial theorem and combinatorics and like, what else? Oh, geometric series and all that. Not too bad, not too bad. So this is the rule you need if you want to follow along with AI proofs. If you want to do Coursera courses, then you will need this. He will say the same thing. If you don't want to learn it, it's fine. Don't worry about it. The key concept is just this thing. How much output changes with a tiny change in input. So the rest of the lesson, Maurice, do you have your hand raised?
Yeah,
Sorry,
I have
I missed
a
you.
question. With the last example, how did you get the -4 exponent?
Yeah.
Go from 1 over 64 to b to the power of -4.
Yeah. So whenever we have an exponent, we go -4. So we want to subtract 1. So if it was 3, then we subtract 1 and get 2. Over here, we had -4. Yeah. So we brought the -4 up front, and we subtracted 1 from -4 to get -5.
But before that, how did you get from 1 over 64?
That's B.
Oh, okay.
Sorry.
Yeah,
Yeah.
okay, I get it now. Yeah,
B to the 4. Yeah. We use this rule up here.
yeah, okay, I get it now. Okay, thank you.
All right, Sierra, that's fine. There's a bit more, but you can see the recording afterwards. Aditya?
Yeah, so the input of the derivative function thing, which is inside the square brackets, that is the function of the line. Is that right?
Yeah. So this, let's say f of x was, this is the input, and the output you get by squaring the inputs. So when you don't define a function like y is equal to x squared, then you could say, okay, let me just shove it into the square brackets. And it's kind of like this goes in place of y. It's just we haven't defined it yet. We could also say
Oh,
y is equal to x squared. And after we defined it, then we could just say dy by dx is equal to 2x. Yeah,
oh, okay.
sound good? Alrighty. So that is the big power rule. That's the big thing you have to memorize. After this, there's only one more key concept, and then the other one's a minor one. So I'll just quickly explain the minor one before we wrap up this video. The minor one is called the sum rule. It's this mysterious phrase. Okay, this is the rule. The derivative of the sum is the sum of the derivatives. What does that even mean? That's what my teacher said to me. That's what his university teacher said to him. Both my teacher and we both agreed this is like a dumb way to phrase things. So let me instead say it with an example. This looks like philosophy, by the way. If you've ever read like Tao Te Ching, this is like Taoist philosophy right here. So let's say I have this equation, y is equal to 3x plus 7x, all right? It is the sum of two terms. Yeah? Sum of two terms. Now, obviously, you know that you can simplify this to y is equal to 10x, 3x plus 7x, 10x. So let's try taking d by dx of 10x, yeah? So we're taking, again, the derivative of this equation, y. We're saying d by dx of 10x. So this is obviously, not obviously, it's hidden. It's 10x to the 1. We bring the 1 out front, and then we take whatever's left, 10x, and then we take this exponent and subtract 1 away. So 1 minus 0 is just 0, which means we have 1 times 10, and x to the 0 is also 1. So 1 times 10 times 1 is just 10. Sound cool? So here's what I'm going to do. I'm going to give like a little bit of a strange thing. So what we did was we took the derivative, okay? We took the sum of these things and we took the derivative. So what we did was we took the derivative of the sums. What if we took the sum of the derivatives? So instead of adding these together into 10x, what if we took the derivative of each and added those together? So here, we added these together first and then took the derivative. Here, we're taking the derivative first and adding them together. Well, here again, this is 1, this is 1. So I bring the 1 out front, and then 3x to the 1, that turns into x to the 0, which is just 1. So I have 1 times 3. And then I can add here. I can add here. All right, so 7x to the 1. So we'll bring the 1 out front, and then 7x, except x to the 1 turns into x to the 0. That's just 1, like we saw here. X to the 0 is 1, so we'll just leave it as 7. So we're saying 1 times 3 plus 1 plus 7, 1 times 7, that's just 10, yeah? Hey, 10 here, and 10 here. That's what the sum rule says. Whether you take the sum first, and then you take the derivatives, or whether you take the derivative first and then take the sum, you're getting the same thing. Is that making more sense? Sum of derivatives, I don't even know. Okay, yeah, this makes sense, right? Whatever that is, I don't know. This makes sense, right? Cool. The reason this is important is sometimes we can't simplify. We can't say 3x plus 7x equals 10x. So for example, here, again, I switched up the variables. It doesn't matter. It doesn't, like, variables can be whatever. We're saying b is equal to a squared plus 2a plus 4. We can't collect any like terms here. Over here, these were like terms. Over here, there is not. But the same rule still applies. So even though we can't collect the like terms and then take the derivative, we can still like do the opposite. Just take the derivative of each term individually. So if we want to take the derivative of the whole thing, that is equal to the derivative of the first term over here, and the next one over here, and this one over here. And, you know, after we get the derivative of each, we can add it together at the end. Make sense? Yeah? Maurice, can you walk me through it? What do we get?
But so
First one?
there you would get 2
Mm-hmm.
and then in brackets a, and then is it to the power of 1?
You got it. So bring the exponent out front, then take whatever you have, multiply it, and just reduce the exponent by 1. Next one is this one. So 2. Then there's a imaginary 1 out here. Aditya, you want to go through it?
Yeah. 1
Out front.
times a to the power of no,
8.
2a to the power of 0.
There you go. You got it. You got it better than me. I can't even write it. 2a to the power of 0. Remember, a to the 0, that is just equal to 1. And then finally, remember this tricky one? Arjun, are you feeling confident? Or would you like me to do it?
It's just going to be 0.
It is just going to be 0. So this is imaginary a to the 0 multiplication. Bring the 0 up front. And then the rest you just put in here, 7a, and subtract 1. Except if you multiply by 0, it's automatically equal to 0. So you have all of these things multiplied together. Where's my white? Yeah, here we are. So this is 0, it just goes away. We're left with 2a to the 1, so that's just 2a plus 1 times 2 times 1. So that's plus 2. Yeah. This is all the sum rule is saying. If you can't combine the like terms, just take the derivative of each of the terms. Bueno? Hopefully that wasn't too bad. So we have one last major rule. It's called the chain rule. It's really important. It is extremely important. So I'm going to split that into a new video. All right.